So Roy, it's 9:45. We wanted to reconvene, so floor is yours. Go ahead.
All right, thanks, Edmund. So for this session, I'll be walking you through accelerating your machine learning workloads with the Intel AI Analytics. I'm Roy, and I'm an AI software engineer at Intel. So some notices and disclaimer regarding the performance numbers that will be showcased for the slides and the demos, just for housekeeping. And this is the agenda for this session. So we'll start by having a quick recap of the Intel AI Analytics Toolkit. We'll then cover the Intel distribution for Python. We'll then talk about the Intel distribution of Modin and how it accelerates pandas. Then we'll look into the Intel extension for scikit-learn and how you can accelerate your training and inference with this extension. And finally, wrap up with the Intel optimization for XGBoost. So I'll briefly recap what's been covered by going over the Intel AI Analytics Toolkit. So this is a toolkit that's meant to accelerate your end-to-end AI and data analytics pipelines with libraries that are optimized for Intel architecture. So as you can see on the right, we have two main subgroups, grouped into deep learning and machine learning. For deep learning, we offer the extensions or the optimizations for the deep learning framework, such as the Intel optimization for TensorFlow, for PyTorch, and the Intel neural compressor that enables you to compress your model and perform other tasks such as pruning the knowledge, like the distillation and low precision, like convert to lower precision. For the machine learning bit, the main components are the Intel extension for scikit-learn and Intel optimization for XGBoost. So these are powered through Wandel, and you get better performance on Intel hardware through these extensions. And to accelerate your data frames and data analytics pipelines and ETL operations, we offer the Intel distribution of Modin. We've also done work to optimize the core packages that are used in Python, such as NumPy, SciPy, and Number, and we'll look at this in detail in the next slide. So the toolkit is aimed at data scientists, AI researchers, ML and DL developers, and AI application developers, and you can use it for training and inference to accelerate both tasks that you're working on. So how does the layered API look like from the libraries and the kernels to the tools that interact with the optimizations? At the bottom, we have the various optimized libraries and kernels, and the ones that are important to us today are Wandel and OneDNN. So Wandel has the optimizations for the classical machine learning packages highlighted in green. So through the Wandel, you have the DAL4Py, which is a Python wrapper to interface to Wandel, and this has the optimizations for scikit-learn and XGBoost. For deep learning, we have OneDNN that has optimizations for TensorFlow and PyTorch, so optimized kernels for deep learning layers that are implemented in OneDNN. And then, you can then interact with this through various IDEs or user applications to develop your machine learning workloads. So what's the benefit of the Intel AI Analytics Toolkit, and why should you use it? The first benefit is to accelerate the performance of your machine learning workloads across Intel CPUs and GPUs with tools and components built using the OneAPI tools and libraries. So these are Wandel, OneMKL, and OneDNN that offer optimized kernels to accelerate your machine learning workloads across CPUs and GPUs. The other main benefit is it streamlines your end-to-end workflows. It's a one-stop shop for all the AI software that you need to develop your workloads for all stages of your ETL pipeline, from data processing, training, inference, and all this plays well together, and you don't need to integrate multiple packages from different sources, which is a headache and is a huge pain point when working with Python packages. So it's a one-stop shop that you get all the packages that you need to develop your AI workloads. And finally, it enables you to accelerate your development. So these are drop-in replacements for Python packages with minimal to no code changes. And this is the premise that we have for all our extensions or optimizations. They are designed to be drop-in replacements such that you just import the package and then no further code change is required to your code base. So With a simple import of the package, you're able to attain or achieve the speed up that the extensions offer. So drop-in replacements with minimal to no code changes that's meant to make the work of the developer much easier to integrate these extensions. We'll then look at the first component is the Intel distribution for Python. So Python is the most widely used programming language in this day and age, and it's used widely across machine learning and HPC. Thus, it's imperative that we offer peak and optimal performance for Python on Intel hardware. So with the Intel distribution for Python, we enable you to develop fast performant Python code with a set of essential packages that we optimize for Intel hardware. And on the right, you can see, for example, some of the packages that we have optimized. For NumPy, we have the NumPy and SciPy a number here that have been optimized, for your numeric and scientific work. The scikit-learn and XGBoost through DAL4Pi for machine learning training and inference. And to accelerate your data frame, we have modding that accelerates pandas across multiple cores, and you look at this in more detail. So within the Intel distribution for Python, we've optimized more than 100 packages that you get best performance for this on Intel hardware, and they play well together, in order to accelerate your workflow. Let's take a look at an example of how this is accomplished with NumPy and SciPy. So on the right, we see how, like Python enforces a global interpreter locker, and this has the downside that then it is single-threaded, right? So this is a performance issue. And NumPy gets around this and offers some multi-threaded multi-core through the BLAST API, but still it's not really optimized for the underlying hardware optimizations. So how do we improve the performance for NumPy and SciPy? We do this by building the NumPy package with the 1MKL, and this gets around the BLAST API, like the performance issues that you have through better performance and vectorization. And some of the dimensions that you can see on the right is, so we replace the BLAST and LaPrac core computations with 1MKL. We also have a fast Fourier-based implementation of this in 1MKL, better vectorization, leveraging the Intel C and Fortran compilers, a better format for the memory allocation, and improved threaded memory copying mechanism that then will result in better performance when you build NumPy with 1MKL compared to using the BLAST API. So this is one way that we've been able to improve the performance of NumPy and SciPy within the Intel distribution for Python, and you can test this by comparing the performance of NumPy in the stock version versus running this in the Intel distribution for Python. So the first component that we look at, so how the presentation is laid out, we're going to look at each stage of your deep learning or machine learning pipeline, and the first step is working with the data, the ETL operations. So for this, we have the Intel distribution of modding. And basically, to set some context about this, it's meant to accelerate your Pandas workloads. So the issue that we see here is Pandas does not scale efficiently to larger data sets. And here we see that, as the data size increases up to a threshold of around 100 MB of data, Pandas is easy to use, provides good, and good scalability up to 100 MB of data. However, as you exceed this, the scalability becomes an issue, and the other alternative is then, switch to Apache Spark, which offers better scalability. However, you have to change or develop a whole, you have to write your entire code base, right? So you have to switch the API from Pandas to Spark, and that's, a whole new learning curve for developers who are not familiar with Apache Spark and how to implement this. So how do we address the performance scalability issues for Pandas while making it easy for the developers to use the same familiar API? This is where modding comes in. So modding enables you to achieve good scalability with your Pandas workflow while maintaining the same API. So we use the same familiar API for Pandas, and all you need to do is just import modding as a package, and you'll achieve good scalability up to 1 terabyte of data and beyond, and also use the same familiar API. So you spend the time that you will have used to change the workload API and use it to improve, you can then spend this time to then fine tune your training and inference as you have to switch from one, like from Pandas to Apache Spark. So Modin offers the scalability and the ease of use that's familiar with Pandas. So how does it look like in terms of embedding this into your application? So basically, to recap this, it enables you to accelerate your Pandas workloads across multiple cores and multiple nodes. And all you need to do is import modin.pandas as PD. So this is the single line of import that you need in order to leverage modin optimizations in your Pandas workflow. And like I mentioned, no upfront cost to learning a new API. We use the same familiar Pandas API for the work, and it's well integrated with the Python ecosystem. So you can use other packages that you use in your workflow, scikit-learn, XGBoost, and other tools that work well with Modin. It's also integrated with the Ray and DAS clusters, so you can use this if you have a big cluster of machines. You can use this on your Ray or DAS cluster out of the box, and it will also run on the laptop you have, which is a multi-core machine. So you can run it from your local device to your big clusters out of the box support. So we'll then look at how Modin works and how we get the performance improvement versus Pandas. So on the right, we see how Pandas looks on a big machine, right? You have a multi-core machine or a multi-CPU machine, and Pandas only runs on a single CPU at a time. This translates to poor performance, and you don't really utilize your system efficiently as you should because you only run on a single CPU. However, if you switch to the Modin API on your big machine, you see that we get full system usage across all the CPUs, and this automatically translates to better performance and accelerates your data frames work. So Modin transparently, it will distribute the data and computation across all the multiple cores, which Pandas does not do. It only does this a single core at a time. And to use Modin, more importantly, you don't need to know how many cores the system has, and you don't need to specify how to distribute the data. All you need to do, as we mentioned, is just import Modin into your workflow as shown here, and that will be able to, you're able to then get the optimizations for accelerating your data frames. We have an example of a code snippet here showcasing the performance comparison for Modin versus Pandas, and this is a simple ETL function. So just to, for ETL, what that means is extraction, transform, and loading of your data. So it's a data processing step that's widely used across data processing. So we read a CSV file, and then we run a group by to group by some column data, and we measure the amount of time it takes to execute this in Pandas and in Modin. So to run this in Pandas, we just remove this Modin bit and import Modin.pandas as PD, and then to run it in Modin, we just add the Modin bit here. And the dataset size is about 2.4 gigabytes. And on the right, we see a plot of the performance comparison, where the same function with Pandas takes about 340 seconds, and in Modin it takes about 31 seconds. So it's about a 10.8x speedup. And if you're able to accelerate your ETL functions, which we typically see are a huge bottleneck in data processing pipelines, then this translates into an overall improvement in your workload's execution time. So through the single simplified import of this package, you're able to accelerate the data framework on Pandas and achieve good scalability across multiple cores, better system usage, and this translates into better performance. The next component we'll be covering is the Intel extension for scikit-learn. So scikit-learn is one of the most widely used packages for machine learning, and this is because of its simplified and efficient tools for data mining and data analysis. Built on top of NumPy, SciPy, and Matplotlib, works very well with these packages, and it's used widely across various tasks such as classification, regression, and clustering. So it's imperative that, given its wide adoption and usage across the industry, we also optimize this extension, this package, and offer the best performance on Intel hardware. So how do we optimize scikit-learn? We do this through the Intel extension for scikit-learn, and how this is done is we'll look at an example of how we implement a support vector classifier in your code base. So you'd first, in your common or vanilla scikit-learn implementation, you will import the support vector classifier as shown here, then create your training and test dataset, perform the training, and then run the prediction, right? So this is a simplified workflow of how your common scikit-learn works will look like. To do the same with the Intel extension for scikit-learn, all you need to do is import 2 lines of code. So from sklearn-x, import patch scikit-learn, and then patch scikit-learn. So what this essentially does is we have various optimized code or the algorithms that we have in like scikit-learn. We have the various optimized versions within the Intel extension for scikit-learn, and this will replace the native support vector classifier with the optimized version in the Intel extension for scikit-learn. And then everything else remains the same. So the rest of the code of your workflow remains the same. And all you need to do is import the 2 packages as shown here. So patching basically replaces the optimized, the default versions or the implementations of the algorithms you have in the native scikit-learn with the optimized versions we have in the Intel extension for scikit-learn. And this is available through Conda and pip. You can install the packages shown here, and then you're able to leverage and work with this across your training and inference tasks across scikit-learn. So let's look at performance comparison. How does it compare to using the Intel extension for scikit-learn versus using the stock version or the original version of scikit-learn? So here, this is for training, where we compare this on a CASTIEL Lake machine. And for a DB scan algorithm for this data set size and shape, we see about a 4.1x speedup. As the number of columns increases, we see even a more significant speedup, about a 322x speedup compared to the original version of scikit-learn. And this is the same story across the board. We see the same for k-means. We have about a 50x speedup here, a linear regression as well, about a 99x speedup. And it's the same story that's translated across the board, where we've optimized the training for most of the widely used algorithms in scikit-learn, that you're able to get better performance here and accelerate your training workload. So we see it's the same case for the support vector classifier, Higgs dataset, and all the work that we've done to optimize the training algorithms. We have the same comparison for inference. So inference is also quite important, and we've done the same work to optimize the inference. And here, the speedup is more significant. For example, with k-means, we see about a 72.3x speedup for this dataset size and shape. We also have even more significant speedup for the KNN brute force, where we have about a 4,000x speedup, and that's the same case across the board for all the other algorithms in inference. So definitely, showing some significant performance improvement to accelerate your inference tasks. And this ultimately translates to lower TCO. If you're running your inference in the cloud, you're able to do much more inference tasks or execution at a reduced cost, as you're able to accelerate and reduce the time it takes to run a single inference by using the Intel extension for scikit-learn. The last package we look at and delve into is XGBoost. So to give an overview of XGBoost, it's a widely used, it's a boosting task that's based on the decision tree, which are base learners. And by building a multiple weak learners, you're able to then have an optimized way of making better prediction and classification and regression tasks. by using this approach. Because of the way you build the multiple trees for the classification and regression, it is compute, you know, it is very heavy to run the training and inference because of the number of parallel trees you have to build at a time. And thus, this results into being a compute intensive workload. It's also very highly accurate, and this is why it's widely used across the industry. If you look at Kaggle, it's one of the most widely used algorithms for all the tasks, even outperforms deep learning in a number of scenarios. We have a number of known implementations for this across XGBoost, LiveGBM, and CatBoost. And XGBoost was the earliest and also still the widely used approach for gradient boosting. So we look at how we've optimized XGBoost in order to accelerate your gradient boosting work. So how we've done this is in two parts. We've optimized both the training and inference. For training, we've automatically upstreamed all the optimizations into the XGBoost repo. So you don't need to make any code changes or any modifications into your XGBoost training pipeline in order to leverage the Intel optimizations. This is done automatically out of the box, and we've upstreamed this into the XGBoost GitHub repo, and it's built with the Intel optimizations. But it's still important to look at what are some of the optimizations that we offer, even as it's built automatically. So the first one is, for example, the memory, like the prevention to mitigate irregular memory access, as shown here. So you fetch data ahead of time, and this will prevent any irregular, like the memory access and any stalls in the pipeline. We also use the assign int 8 or assign, as opposed to the assign integer 32, and this also results in a faster speedup because of a smaller memory data for this, as you pack it in a smaller package, and that translates into a faster execution. Then also the use of SIMD instructions of a single instruction on multiple data instead of the Scala code. So this also be able to work on multiple data at a single run and process multiple data. Thus, through the vectorization, you achieve better results. Better loop unrolling and parallelism is also part of the optimizations that we offer. And finally, also the usage of the AVX512 instruction, where being hardware aware of the hardware capabilities, such as if the hardware has AVX512 instructions, it will leverage that, or if it has AVX2, it will also use the existing hardware instruction for the runtime, which was not available before we did the optimization. So you could have a machine that supports AVX2 and AVX512, and because that version of XGBoost was not aware of the hardware capabilities, it will still execute maybe the runtime in AVX2 instead of working with the more powerful and performant AVX512. So this is just showing some of the work that has gone into optimizing the training workflow and how it looks like for the training optimizations for XGBoost. The same work has been done to accelerate your inference. So inference is equally important. And for this, we do this through the DAO4Pi package, which is the Python wrapper into one DAO. So how you typically look at it is, like we mentioned, we've already upstreamed all the training optimizations. So the training workflow remains as it was. So you just train XGBoost model, xgb.train, as you would. Then to run the inference, we've done this through DAO4Pi. So we import DAO4Pi as the package, import DAO4Pi as D4P. We then create our DAO4Pi model from the XGBoost model. So get GBT model from XGBoost, and we pass the model that we trained here as a DAO4Pi model. And then to do the prediction, whether it's classification or regression, we just use the same function call in the DAO4Pi, the d4p.gbt underscore classification. If it were regression, this will be underscore the regression and prediction to run the test. So the 3 lines of code, this is all you need to do in order to accelerate your inference with DAO4Pi. Import DAO4Pi and create a DAO4Pi model from the trained XGBoost model, and run your prediction and inference tasks within the DAO4Pi functional calls. And basically, like we saw earlier, in inference, you have better memory like usage, AVX512 like usage as well, and beta L1 and L2 cache locality to avoid any cache misses, and thus this translates into a better performance. On the right, we see performance comparison for running the airline dataset. It's about 2.31 M rows with XGBoost and working with XGBoost plus the DAL4Pi backend for inference. Here we see that we achieve about a 23x performance speedup when we run the inference with the DAL4Pi backend. And it's also important that no accuracy is lost. So one premise that even as we optimize all these packages, the accuracy is not impacted whatsoever. You get the same accuracy, when working with scikit-learn versus, the Intel extension for scikit-learn. Same applies to working with the DAL4Pi backend to accelerate your inference, as showcased here, versus native XGBoost. So the accuracy difference is 0, as you can see here, but you get a 23x performance speedup to accelerate your inference. So I'll then switch into the demos that we have for our AI analytics and showcase how you can get started and try out the various packages that we've showcased and how to, where to get this. So I'll share my screen again. Just let me know when you can see. Can you see my screen? Can you see the browser?
Yes.
Yes. So if you go to github.com/the one API source, one API samples, we have all the samples you have for one API, and these are across all the toolkits that you have. And for today, of key interest for us is the AI and analytics package. So if you go into the analytics, we have the demos and samples grouped into the getting started samples, so how to integrate this into your workflow. Then looking at so this is, like basically how to get started with XGBoost, how to embed the DAL4Pi for inference, TensorFlow, PyTorch, Modin, and so on. Then you have the features and functionality. So these go into more details about the performance comparison for our optimized packages versus the original or stock packages. So here it's mainly focused on the performance comparison. And then we have end-to-end workloads that look at how can you build a full pipeline leveraging Modin for the ETL, scikit-learn for training and test split, for training and inference, or XGBoost as well for training and inference. So how you can build a full pipeline using the optimized tools and packages. So the first package we'll look at, in the interest of time, I had pre-run or I had executed the cells in the Jupyter lectures ahead of time in order to have ample time to walk through the demos and showcase how to integrate this and see the performance comparison for the packages. So the first one we look at is Modin, and this is one of the samples that's available in the one API repo. And we first import all the required packages and dependencies, so the NumPy, matplotlib, and time. And like we saw earlier, we then import pandas and import modin.pandas as PD. We then create a synthetic data set that we'll use for the benchmarking here, and we save this into a CSV file. So this will perform all our data frame tasks on this CSV in order to compare the performance for pandas versus Modin. The first task that we do here is we compare the time it takes to read the CSV in pandas and look at the same in Modin. So a pandas df, a pandas.read CSV, the CSV file, and we do this for the first 256 rows. And here we see that it takes it takes a total of 11.1 seconds to execute this in pandas. And we then do the same with Modin, so pd.read CSV, as we saw earlier, and this takes 3 seconds. So 11.1 seconds to 3 seconds, that's about almost 4x speedup. And for better visualization, we create a function here that we can use to visualize the performance comparison. So it's just a function to plot the time for both Modin and pandas. And we do the same here as we see. So we execute the read CSV in pandas and do the same in Modin. And we see with pandas, it's about 10.6 seconds, with modern 4.36. And this is the plotting of the execution time. So I'll see if I can zoom out a bit for this. Okay, yeah. So you can see it's okay. I'm trying to zoom out to. Right. Okay. So it's not able to zoom out because of the double monitor. But yeah. But here we see, the performance speed up is quite significant from 10.6 seconds to 4.36 seconds when working with modding for this task. Then we'll compare other data frame operations. So you have the same API for pandas in modding, and of course, you can run your pandas functions in modding. One example of this is the apply map function in pandas. So we do this with a lambda function for our data frame. And here we see the pandas time it takes to execute this in pandas is about 17.14 seconds. And doing the same with modding, this is about a 2.29 seconds. So comparing the speed up here, we get a 7.48x faster than stock pandas. And these demos are available in the 1API samples on GitHub, so you can get access to the demos and just run the cells, for your own comparison and to see the performance speed up here. Another one is to join two data frames through the when you have when you're working with one data frame from one source and another one, it's a common function that you need to combine the two data frames. So we can concatenate the two data frames as shown here. And with pandas, this takes about 0.235 seconds. And we do the same with modding for the concatenation function. And we get 0.041 seconds. And here we see that a modding was 5.6x faster than stock pandas. So in this case, you're able to see how, you're able to get at least for most functions up to 5x to even 7x speed up when you switch from pandas to modding. And this is quite significant because in all our work when working on machine learning, one of the main bottlenecks is working with the data and the data pipeline of pre-processing, post-processing functions. That's where we see, as a huge bottleneck, and with modding, you're able to accelerate this stage of your pipeline. The next demo we'll look at is the Intel extension for scikit-learn, which was the other component that we had a look at after modding. So this is how you're able to accelerate your training time with the Intel extension for scikit-learn on the adult data set. So we're going to use a support vector classifier comparison with Intel extension for scikit-learn versus the original version of scikit-learn. We first import all the dependencies that we need, then we get our data set. So the adult data set from here from OpenML, and then we create our test and training data set here. And use 20% of the data as our test set. So we saw earlier that all you need to do to leverage or use the Intel extension for scikit-learn is from sklearn import patch scikit-learn and then patch scikit-learn. So this is what you need to do, and you'll get the message that Intel extension for scikit-learn is now enabled as shown here. We then create our parameters for training. So we use a radial kernel for training, and we set our gamma parameters as well to be a scale function. And here we then train it with the Intel extension for scikit-learn on the dataset, and this takes about 23.46 seconds to fit this on the training and test. To fit this on the training data, we have about 23.46 seconds. And we do the same, we also make predictions with this. So we make the predictions just to cross-check on the correctness and the accuracy of the data, right? So this was to showcase that there's no accuracy difference when you use the Intel extension for scikit-learn versus using the original version of scikit-learn. So we look at the precision, recall, and score, and we'll compare this when we run the same algorithm with the original version of scikit-learn. So using original scikit-learn, we first need to unload the Intel extension. So all you do here is from scikit-learn import unpatch scikit-learn and unpatch scikit-learn. So this removes this from our kernel, and we default now to using the original version of scikit-learn. Then we run the same training function that we did earlier, and you see here that it takes about 662 seconds, which we saw with the Intel extension was 23 seconds. And we also do the accuracy check for the results where we see the precision, recall, and F1 score for the same. So let's plot the performance comparison. So it took about 600 seconds, as you saw, to train with the unoptimized or the original version of scikit-learn. And we had about 23 seconds here. So this is about a 28.2x acceleration or speed up for your training. And this is quite significant if you're able to, speed up your training time by such a factor. For the accuracy check, so we compare the accuracy difference for Intel extension for scikit-learn and the original version, and you have a 0.0 accuracy difference. So even with optimizations, the accuracy is preserved, and you get the same results for both the extension and the original version. So that's important as well to note. And finally, we look at the XGBoost package and how we accelerate inference for XGBoost work through Pi. So like I mentioned earlier, for training, this is already upstreamed. So you'll get by default all the optimizations for training in the XGBoost package from source. So we first import all the necessary data in packages. So we import Pi, XGBoost NumPy, pandas, time, and matplotlib. We then create our read CSV function that we'll use to read our train and test datasets. So we already have the train file and the test files uploaded. We then read our train and test files and create our D matrix for XGBoost train and testing dataset. Set our hyperparameters for XGBoost, and we train XGBoost like we typically do. So this is the same for both. For training, the workflow remains the same on the Intel side and the native XGBoost side because the optimizations are already embedded into the main package. For inference and prediction, that's where there's a difference that you have to import Pi. So here we'll make the prediction using original XGBoost, where we just run the XGBoost.predict on the test dataset, and we measure the time it takes. We also look at the errors. So this is used to assert or compare the accuracy difference as well that we look at and compare to using Pi for inference. We do the same now with Pi. Like we saw earlier, we get the XGBoost model and pass it here to create our Pi model. We then just create our classification function. So here we pass in the number of classes, and we are looking at the class labels, and we work with the flow data type. And then all you need to do is just run the compute in order to run the test on the inference. So we also measure the time it takes to run this and check for any errors that will compare for the accuracy results. And then we assert this, like comparing the XGBoost error count to the Pi error. So this is important for the accuracy check. And finally, we look at the results that we get. So here, for the XGBoost prediction results, for the first 10 rows, these are consistent, as you can see. And, the error count for XGBoost is 10. The Pi error count is 10. The accuracy score here is 0.99. The same we have is 0.99. The only thing that differs is the prediction time here, where we have 0.04 in XGBoost, and Pi we get about a 0.03 time. And we can visualize the speed up here, where the time it takes with XGBoost is plotted here, and the same with Pi. And this translates into about a 1.6x speed up when you use the Pi backend for your inference. And to visualize the accuracy, here we see that there's a 0.0 accuracy difference. You get the same accuracy results when using Pi backend versus using the XGBoost backend for your prediction. So this is a summary of the demos and showing the performance speed up that you get with the packages that we have. And just to quickly wrap up everything, and so back to the presentation for the last slide. Can you see that slide? Do you see the presentation?
No.
Okay, let me just a second. Share. Okay. Yeah. So to wrap this up, as the main takeaways for you regarding our machine learning optimizations within the analytics like toolkit, we offer tools to accelerate each stage of your pipeline. So this is through the Intel distribution for Python to accelerate your NumPy and SciPy operations, modding for the training and data framework, and Intel distribution for scikit-learn and XGBoost to accelerate both the training and inference for your various machine learning workloads. And like you saw as well, these are drop-in replacements with minimal code changes to speed up your development. So it's not a steep learning curve to embed this or leverage this into your workflow. All you need to do is import the packages and the rest of your workflow remains the same. And finally, the packages are easily available through Conda, Pip, and Docker. So you can choose to either install the AI Analytics Toolkit as it is, or install the individual packages through Conda or Pip, and you're able to get the optimization. So I hope this has been helpful in showing how you can accelerate your classical machine learning workloads. And yeah, any questions at this point?